freely through the device. As the flow increases, the pressure drop also increases. Remember we said as the velocity increases, the pressure drop also increases. So it decreases that downstream pressure area here on this arrow and decreasing the forces acting upon the plunger to hold it open. So what happens is when this signature in here, this pressure signature gets to a particular, or I guess when this pressure map gets to a particular signature is a better way to say it, and when the force produced by the downstream pressure added to the force produced by the spring becomes less than that force on the upstream pressure, then what's going to happen, if you look at this upper square right here, the excess flow valve, it snaps closed. So it reaches a particular signature where those forces flip over and then the valve closes very, very quickly. It's designed to close very quickly once that signature is met. And then I mentioned just briefly that all of our devices are bypass devices, meaning automatically resetting devices. And so whether it's automatic reset or not, as soon as the pressure on the downstream side comes back to equalization, in other words, we get back to a pressure signature where the forces flip back over and equalize, what's going to happen is that EFV will just snap back in the open position because now the forces of the spring and the downstream pressure are enough to overcome the forces by the upstream pressure. And so your EFV resets. So what does this mean? Well, it means the device actuates when a specific pressure differential is created. So as we looked at that pressure signature, really this is a graph that shows the trip point of an excess flow valve. And we said predetermined condition earlier on, meaning that at different pressures, the trip point in standard cubic feet per hour, that device is going to change at different inlet pressures. But you can see that the pressure differential really remains constant, and that's true for different sizes of excess flow valves, whether it be large or small. You've got that pressure differential signature is remaining constant, but your EFV is going to trip at different flow rates depending on the conditions. And that'll become a little bit clearer, but that's what we mean by predetermined condition. So the principle of operation remains true as the size of the device and the trip point of the device are increased. Okay, so let's move on here to the next slide. Again, what does that mean? Well, in other words, what we have really is a pressure differential valve. It's a valve that understands the pressure differential across it because it's sensing those pressures. And as the pressure changes into the signature that overcomes the forces inside the valve is going to either close or open back up. So when does it become an excess flow valve? We refer to them as excess flow valves. When does that happen? Well, it happens when it's properly sized and designed into our service system. It's really a cooperation of the device itself and its application into the gas system that makes it the excess flow valve or the safety device that we have designed it to be. So the device itself doesn't really know anything about excess, as we know. As we've talked about it, we said it's a dumb device. It's set to do a particular thing at a particular condition, and it's going to do that, but it doesn't know what excess is. We have to determine that through our design and application of the valve into the system. And we'll talk about ways to do that here in just a little bit. So we talked a little bit about reset and bleed by. Bleed by models have this small passage that allows the gas to continue to flow through the excess flow valve even in its closed condition. So we say it reduces the flow of gas on our valve. It doesn't necessarily stop the flow of gas. And that's got to be less than 20 standard cubic feet per hour by code. Now there are positive shutoff models and opportunity to have a positive shutoff model where you'd have to reset the EFV manually through some sort of a back pressure, a compressed natural gas, or some other means. But most of the devices used today are automatic reset valves. So how do we determine the correct EFV to be used for a particular application? And we're going to go through some of that now. If you had questions on operation, just go ahead and jot them down as a reminder, and we'll get to those as we get to the end of the webinar. So ASTM F2138 suggests that an EFV should be selected with a trip flow at the distribution system minimum pressure above the maximum customer load and above meter capacity. On smaller pipe sizes and lower supply pressures, sizing is critical. There are really three important considerations. How long can my service line be and still guarantee the actuation of the EFV with a complete breakage at the end of the line? Meaning, will I cover my entire service line length with this excess flow valve? If it's open to atmosphere, will there be enough will there be enough flow to allow that pressure signature to be reached at the EFV and have it trip? And then at maximum load, will my customer have enough pressure at the regulator to keep things going? What's my minimum pressure that I need at my regulator? And with the service line length that I have in the EFV that I've selected, will I be able to keep that pressure at the regulator with the anticipated load for that particular structure? Is the trip point above the maximum expected load at the minimum supply pressure? So you want to have that minimum trip point above what your anticipated load is at that minimum system pressure. So those three considerations you need to keep in mind now as we're looking to apply a particular device into a particular system. So let's look at that real quick. We'll look at a chart here for a particular series EFV. And because each EFV, as we said before, wants to trip at a predetermined level, it's very specific to the conditions. So this chart here shows different inlet pressures along the bottom of the graph and then different flow rates upon the y-axis. And this is for a series, what we call our Series 350 EFV. And in most cases, you see that we very cleverly name our series at the minimum trip point at 10 psi. But again, you have to look at whatever pressure it is that your system is operating at when you're sizing these things. So let's say we have a normal system pressure of 45 psi-G. We have a meter capacity that's going to be our maximum anticipated load at 425 standard cubic feet per hour. And we're going to use a half CTS service line. Okay, so we've got a, I'll just click on that. It should show us our points here on our graph, and here it shows us at 45 psi what our trip point is going to be at that pressure, and we're about 28% above the anticipated load, so we're well above that. And if we use our maximum trip point is going to be 817 standard cubic feet per hour. So if we look at this dotted line on this graph, that represents the maximum trip point. Code allows a 50% cushion between minimum trip point and maximum trip point. And so this graph is showing that the maximum trip point that this EFV could trip at would be 817 standard cubic feet per hour at this 45 psi inlet pressure. Now, in reality, excess flow valves are typically, designed to trip somewhere in the middle of that range, with the distribution spread of manufacturing variations, so that you always have an EFV that's tripping well within these two limits. But for sake of sizing, we're going to use the maximum trip point because it could trip at that level, worst case. So if we take an equation like the AGT equation, it would yield about 840 feet of pipe length that we could protect at the half CTS service with this Series 350, even tripping at that 817 standard cubic feet per hour. So on surface, this looks pretty good. We've got great cushion here between the minimum trip point and the anticipated load. We've got plenty of service line length that we can protect. But what happens if we look at this now at a system pressure of 12 psi? Our minimum that our system drops to is 12 psi. What you see happens is all of a sudden our minimum trip point drops below our anticipated load. And now the expected load is like 17% higher than the minimum trip point of 364 standard cubic feet per hour. So what does that cause? That will cause what we call nuisance trips. So if there's a demand within the anticipated demand of that structure and your system's at 12 psi and you sized it at 45, you could have this EFV tripping even when you don't want it to, just when someone turns on their pool heater or whatever it is they have connected, and they're just using the amount of gas that was expected to be able to be used, and all of a sudden your EFV trips. So this is why it's very important to start out looking at that minimum system pressure. So if we did that, we're going to change our chart here slightly and go to a series 475 and size on a 475 using the half CTS service line still and the anticipated load of 425 standard cubic feet per hour. Now at 12 psi, you can see that we have a 16% cushion between the anticipated load and our minimum trip point at that 12 psi pressure. Our maximum trip point is going to be 741 standard cubic feet per hour, and we'd still be able to cover about 145 equivalent feet of pipe. Now if we wanted to keep 6 psi, we talked about the fact that we wanted to keep a certain pressure at the regulator. In this particular case, if we wanted to keep 6 psi at the regulator, we would be able to cover 213 feet of half CTS line with the pressure drop in the EFV at 741 standard cubic feet per hour. But because we're actually need to size on that maximum trip point, we're going to use 145 equivalent feet of pipe that we can protect. So if you want to protect the entire service and keep a particular pressure at the regulator, you have to take the lower of the two numbers. So even if you can keep 6 psi at the regulator with a longer service, you have to take the lower in this case here of 145, because that's the maximum line you'd be able to protect and still have the line severed and have the EFV trip if the EFV were to trip at that maximum trip point. So let's look at that graphically. Maybe it'll be a little clearer. If you had a service line, 145 feet of that would be protected if that EFV tripped at its maximum trip point. So again, these are worst case numbers, conservative, but ways that you can use to size. And you have to determine within your own organization what are those cushions that you're going to use between the maximum anticipated load and the minimum trip point, and how conservative you're going to be on the service line length protected. So for residential services, the anticipated load is determined and the appropriate EFV is selected to prevent those nuisance trips that you saw, and to provide protection for the entire service length. So you want to do both. And of course you want to keep the minimum pressure at the regulator as well. So then we can talk about larger EFVs as well for multifamily homes or larger demand structures. I'm not going to go through all of this, but as we all know, there's legislation that came down in the Pipes Act of 2011, Jobs Creation Act actually, that's looking at increasing or expanding the use of excess flow valves into multifamily residences and possibly some larger demand type structures. There's been a lot of discussion on that. We still don't know. There hasn't been a rule, although it's pending, I guess. It's imminent on what exactly that's going to mean and what flow rates are going to be required. But again, we'll just kind of go through some sizing considerations for some of those higher loads. When you get to commercial or industrial applications or higher load applications, sizing needs to be more carefully considered as the load requirements can become more variable. So thought we'd just take a quick look at a chart here, which it looks like this chart's not going to act right for me, but what we have is a initial load down here. Let me see if I can get it to come up. Looks like it doesn't want to come up. Okay, so we're going to look at an initial load of about 48 therms here, or 4,800 standard cubic feet per hour. And if we were to size that for, say, a 5,500 standard cubic foot per hour at 10 psi EFV, you can see at 10 psi we would be, this is a 2 IPS line, by the way, and we're looking at 150 foot of service, 6 psi minimum at the regulator. We would be above that maximum anticipated load of that 4,800 standard cubic feet per hour at 10 psi with our trip point curve. And so initially we may be okay, but if you want to look at the capacity of the service, and part of the discussion in the industry has been, well, just size your excess flow valve to the capacity of the pipe, and that can become a little bit interesting as the capacity of the pipe at those pressures and size can be quite large. As you can see here, 21,524 or in that range. So if we were to size up around 20,000 standard cubic foot per hour flow, or be able to handle a 180 therm type of load, now you're looking at an excess flow valve that has fairly high trip point, and then you have to ask yourself, when is that going to trip? And you can see you have 15,200 standard cubic foot per hour difference between these 2 points. If you size to this capacity and you're really sitting at 48 therms of load demand on that structure, you've got an awful lot of gas that can be escaping in a line if it were severed before it would trip above what that load demand is. And so there has to be, obviously when you're sizing, you have to ask those questions on how far above the load do I want to go, especially as the pipe sizes get larger. What we see, and if I can get this thing to click forward, just threw a couple pictures in here of some 2 IPS pipe and some different damages from a damage database that shows that when 2 IPS pipe or some of this larger pipe gets hit and you have a breach to atmosphere, you don't always have a full open of the pipe to atmosphere or a clean sever where you're going to allow the maximum flow of that pipe. So if you're sizing at the maximum capacity of your pipe, you could get into a situation where you're not going to trip that excess flow valve even with some fairly severe damage. Here it looks like an auger went across this and popped a hole in the top of this pipe. And so you could have in these 3 situations potentially a pipe that is blowing gas but not tripping an excess flow valve if you have set that excess flow valve all the way up to the line capacity. This bad boy over here on the right that peeled back this flap looks like a backhoe tooth. That would likely trip, of course, but there could be many situations where you could have quite a flow of gas then above possibly your demand at the moment that is escaping if you're sizing the capacity. So these are some of the things that need to be considered as we're looking at these larger flow rates and larger sizes, and each company is going to have to make that determination on what's appropriate. But I thought it would be interesting at least to look at some of those issues. So as we talk about sizing, we looked at some of these charts, and and you can use charts, of course, but we like to say there's an easier way. We've built a calculator that kind of helps go through some of this sizing exercises, and the idea is to help or enable our users to be able to come up with those sizing charts that would be useful for them within their system. Everyone uses a different sizes of service lines as their standards, have different system design considerations, but with the calculator you can then build those tables that might be useful for your organization to determine which excess flow valve in which condition, which type of service that you might be installing would be appropriate, and standardize that within your organization. So we'll take a little bit of a look at this calculator, how it works, and what are some of the numbers you can get from it, and some of the things that you can do to build some of these tables within your organization. First, just a couple things about the calculator. The calculator, well, let's go into it. I guess I'll discuss it as we go along. There are several sections of this calculator. You can see up here at the top left, there's a section where you have some pull-down menus for the EFV series that you want to select and the service line pipe size. Both of those are drop-downs that allow you to select particular values. Obviously, you're going to be able to select the EFV series in our calculator that represent the EFVs that we manufacture, and then you can pick the service line pipe size of your particular service. It also allows you to put in what your minimum EFV inlet pressure or system pressure is expected to be that you're going to design around or make your selection around. It allows you to put in the specific gravity of the gas and the temperature. By default, they're just set at the standard rates. And you can see it's just blown up a little bit more where you can enter the inlet pressure, specific gravity, and gas temperature. Now from those entry points, you're going to get some outputs that are typically in the blue fields. And those outputs are going to tell you that with the EFV selected and the pipe size that you selected, and with the parameters that you've entered, what the minimum trip point and maximum trip point of that particular excess flow valve is. And you can see it here in these first two boxes. And it shows up over here on the graph as well. So we have a trip flow chart graph, and it tells you that you've selected 10 psi, and here is your minimum trip point, and here's your maximum trip point. That shows up on your graph as well. In this particular case, there's a 5% cushion that was entered in here, and we don't limit, really what you can put in there too much, and we allow each customer to decide what that what the cushion that they want to have in their system should be, and that's really up to you to determine. But as you see on this chart, at 5%, that means you could have a load, a maximum load of 5,238 standard cubic feet per hour under these conditions. And again, I should point out that this calculator calculates on the maximum trip point. So when it gives you the number of feet protected, it's giving you the number of feet protected based upon that EFV tripping at that maximum trip point. And that's important to understand. We didn't really make the calculator, we made it to be kind of conservative, not as a way of entering into specsmanship of any type. Different companies may present these numbers in different ways. Some may use the median value of the trip range. So they might say that you have a certain protected feet, but their calculations are based on the middle of the range rather than the extreme of the range. And that's okay, but you just need to know when you're using this calculator that everything that's giving you is conservative numbers based upon that maximum trip point. And then, of course, it gives you the service line length protected under these conditions, and it's 1,594 feet of this particular line that's selected here. So that's kind of the layout of this top portion of this calculator, and we'll actually get into the calculator and exercise it a little bit here in a minute. Let's look at another section here real quick though. We have this section of the calculator is new. It's in version 7A, and this will be available online after this webinar. We've added a section to look at the desired load and also keeping that minimum system pressure at the regulator. In the past, this was not in the calculator, and this is something you had to really verify on your own, but now you can use the calculator to kind of double check that as well. And it allows you to put in a number of what the pressure that you want to keep at your regulator is and what that desired load is. And now it'll calculate your equivalent service line length based upon that desired load and that minimum system pressure at the regulator. And it'll tell you how many feet you can protect. And in this case, it's 1,462. So with this same EFV and these same conditions, you would want to use the lower number, even though you could protect more line potentially out to atmosphere at a full sever at maximum trip point. If you want to keep the regulator at a minimum of 6 psi with this desired load, then you would want to have your service line length at 1462 or equivalent length. I should also note that we use the word, you'll see the word equivalent length quite a bit. And what that reason it's equivalent length is because that's considering a pipe all to the end of your service. And we recognize that you may use other fittings to connect up along the way, and you'll have to take those into consideration as far as the loss of those fittings in the system as you make that connection. So this would be just considering the numbers that come off of here, just be considering the pipe from the excess flow valve to the end of the service. If you have a connector that has 15 equivalent feet of pressure drop, then you'll have to take that into account as you're looking at your actual service line length. So what can you do with that calculator before we get into actually playing around with it a little bit and exercising it? What it will allow you to do is build some tables. So you can put in different parameters within the calculator and build tables around your particular service line sizes. Here on this table, you'll notice we've used half CTS, 1 CTS, inch and a quarter IPS for these residential size services. And this table is based upon series up to 1800, series 1800 at 10 psi design pressure and keeping 6 psi minimum at the regulator. Your parameters may vary, but that's okay. You can set those into the calculator as you're building these tables. But what it allows you to do as a company then is very quickly determine which, for which particular type of service that your crews are going to be installing, which excess flow valve have you determined to be appropriate for that particular installation. So if we zoom in here a little bit, you can see for half CTS up to 110 feet with a load of 450, keeps you that 5% margin between your anticipated load and the minimum trip point at those conditions, and also allows you to maintain that 6 psi minimum at the regulator. So if you were putting in a service within these parameters, then you could use the Series 475 in your half CTS line. Looking at the other side, you can see if we get into some longer service lengths, some higher flows, inch and a quarter IPS pipe, a Series 1200 would fall into this range. So it allows you to then select or pre-select, so it doesn't have to be determined at the time, which EFV is going to be used in which classification of service installation. So this chart would be for higher flow devices, Series 1800 to up to 5500. You can see in this particular example I use inch and a quarter and 2 IPS service line sizes, so quite large. But again, it's the same idea. You can build a table that says if you've got a demand expected in 3,100 standard cubic feet per hour, you can protect up to 3,000 feet of line with this CE EFV 3900, keeping a 5% margin and 3,000 feet of protection and 6 psi at the regulator. So you've done the calculations already, you've built your table, and so anything within this range then you've covered for that particular installation. So I'm going to jump back here actually for a minute, and before I go on and get into the calculator itself. I'll try to open that up so we can play with it a little bit. Okay, so here's the calculator. I'll see if I can make this a little bigger so people can have a shot at seeing it on their screen. Does that look fairly visible? I'm asking the people in the room. Okay, so here's the calculator that we were just talking about. This is version 7A. And again, you can see that we have these drop-down menus that we talked about. So let's just do a couple so you can get an idea of some of the things you can do on the sizing side before we move on to some of the other considerations and tools that are in this calculator. So let's say we want to use a Series 775 excess flow valve. We'll have our system pressure at 10 psi. This would say if we're going to use a 1 CT, okay, we'll stay with the 1 CTS service line. Let's make it a 1 IPS just for fun. Okay. 1 IPS, so our minimum trip point is going to be 775 at 10 psi. Maximum at is 1,163. You can see that shows up over here on the graph, and that updates as you make your selection. If you were to go in and change your pressure and say, well, really our design requirements in our system is a minimum pressure of 25 psi, we're not designing to 10, well then it'll update your graph for you and show you that at that pressure, that same excess flow valve is going to have a minimum trip of 983 standard cubic feet per hour and a maximum of 1475. Now, let's say we wanted to keep a 15% cushion on that particular valve, and I'll click out of there so we can hide that note. It's going to tell us that our maximum anticipated load that we could then have at that 15% cushion is 855 standard cubic feet per hour. But the service line length protected, because we're at 1 IPS pipe, fairly high capacity pipe, is going to be quite large, so we're not going to have any issue with most services unless we're putting in services over a mile long. And so that looks pretty good. Now, if we wanted to check out what our desired load is, and we're going to say, well, really, these are loads going to be 800. And we wanted to keep, let's say, 6 psi at the regulator. It's telling us, well, we can have all kinds of length of pipe to do that. So that's not a limiter. But we'll go ahead and we'd still have to figure on the lower number if we were going to try to run a service out that long. But in essence, for most services, obviously, you would have no problem protecting the full length of the service line, having a line open to atmosphere, and having it trip if you're considering this 25 psi as your minimum inlet pressure. If we take that back down to 10, though, again, it's going to readjust. And we're going to see that that 800 load turns red on you because it's telling you that what you had in there before is no longer really applicable to the EFV in this condition, because its minimum trip point is 775, and you're going to get those nuisance trips now if someone tries, to use the full desired load of 800, and your system's at a condition of a pressure condition of 10 psi. So it's saying if you want to keep that 15% cushion, you're going to have to be no greater than 674. So maybe here we're designing for 650 or whatever we want to put in there. That gives the 19.2% cushion, and keeping 6 psi at the regulator, we still have quite a length of service line protected, so we're not going to have any trouble there either for most services that are less than a half a mile anyway or more. So that's how you can utilize this calculator, and you can put in really whatever numbers you need for whatever series. Let's pop into maybe a little larger. Let's go to the 5500 and use a larger size, say 2 IPS pipe. Again, it's going to tell you that at the 10 psi, your minimum flows trip point is 5500, maximum is 8250. Again, we're calculating the service line length that can be protected based upon that maximum number. Here we have a 15% cushion still put in there, so our maximum anticipated load to keep that cushion could be 4,783 standard cubic feet per hour. So if we're really looking at 4,500, it's going to give us a 22% cushion, keeping 6 psi at the regulator. Still have 2,000 feet of service that we can we could protect. So we would use this number here, 1594, so that we could protect that entire service. Should it open to atmosphere at these conditions, it would trip off. Now at this point, I will point out there's another tab on the calculator that's a pressure drop tab, and I'll go through that just kind of real quickly. But this was here for those that want to just know, well, what's the loss due to the excess flow valve under the conditions that I have set in place. And then you do your own calculations on your service line length protected and all the the different configurations you have on your service line with the different fittings, and you do those calculations yourself. And you just want to know what's the loss due to the excess flow valve with the conditions and flow that I'm figuring on. So let's use a Series 775 here, and let's say that EFV minimum trip point is going to be 919 at that pressure that we had set for the excess flow valve. Minimum trip flow rate is 919, and we have an inlet pressure of 20. So if we wanted to set that down to 10, it'd be 775. But whatever you want to set it to, it doesn't matter. But down here is where you get your answers or your results. You can get the result based upon that minimum trip point or on what your desired or anticipated flow is. So if your anticipated flow is really, let's say 500 standard cubic feet per hour, then, and you want to calculate on that and figure out how much service line with keeping a particular regulator pressure, you can see that at the desired flow, your pressure drop is, and I'm having a tough time seeing it from here, but I think it says 0.315. If I'm having trouble seeing it, you guys are having trouble seeing it, I'm going to blow it up. 0.316 psi. But at the trip point, it's 0.758. Obviously, the flow rate is higher at trip point, so you're going to have more pressure drop at that point. So this just allows you to graphically see that in both PSI and in water column. So if you want to just know what the contribution of the loss of the excess flow valve is at the conditions, you can use this sheet to get that information. but most of the time you'll probably stay on this page and you'll just be looking at these considerations that we were looking at before for that particular excess flow valve and your service line condition. Okay, let me go back into the presentation here if I can, and we'll move on past this. I want to make sure we leave some time for questions at the end. So installation considerations. Let's just talk about that here real quick. Let's say we have a system minimum pressure at 10 psig. We have an expected load 7.56 therms, so 7,560 standard cubic feet per hour, roughly, and service line length is 240 feet. So we get out of this chart that we made a little bit earlier, and we'll look down here and we'll say, well, 750 standard cubic feet, and I want to have 240 feet of service line protection here. So I should have a 1 CTS service line, and I can use a Series 1200 to keep me at that 6 psi at the regulator and a 5% margin to minimum trip point and load. So this is where that chart comes in. After you've used the calculator to build your chart, you don't have to go back to the calculator each time. You can just say, okay, we'll use a Series 1200, got the 1 CTS service line. And now we've got this service that we've got set, and this is where there's some things that have come up in the past, in our past history with excess flow valves that I think is important to kind of keep in mind and consider. Early on, as excess flow valves are becoming more and more used, some of the early issues that came up on the installation, we would get calls where the EFV would have appeared to trip, and the customer didn't necessarily want it to trip, and it would happen during the blow off of the service. After installation, they would open the valve up and they would allow gas to flow, and there was some thinking that how quickly you open that valve had an effect on whether or not EFV would trip, and if you open it slowly, that you could keep it from tripping, and if you open it quickly, you might trip it. Some companies have procedures where they purposely want to trip the valve and open up the line to atmosphere and purposely trip the valve to make sure that it's working and then allow it to reset. Others don't. All these valves are tested for snap acting loads at 75% of that trip point, and some at even higher levels. And so how quickly you open the valve is typically not as important as how far you open the valve. So as you can imagine, if you've got your service line set and sized correctly to protect the entire service line should it be open to atmosphere, that you can expect if you open that valve to atmosphere that it's going to do just that. It's going to trip the excess flow valve, and you'll see that by a sudden reduction in the flow of gas, because essentially what you've done is you have you've opened that valve to atmosphere and simulated a breach, although it was at the stop valve. And so as we're looking at this, we want to make sure that it's not necessarily how quickly, but how far you open that valve. If you have a procedure that you don't want to trip the valve, in other words, that's not part of your practice or process to trip the valve to verify its operation, then you'll want to give instruction on how far that valve should be open during this operation so that it doesn't trip. And what we were seeing is oftentimes crews would kind of get into a loop where it would trip, and then they would feel the valve was not functioning correctly because it wouldn't reset, or it wouldn't allow the flow of gas. And then ultimately they would want to dig out the excess flow valve, thinking that it wasn't operating correctly when actually it was doing exactly what it was designed to do, and that is closing when it was open to atmosphere. So some companies have done things like putting restrictors on the end of the valve before they do their bleed off to an orifice or something to restrict the flow, so they could open the valve all the way open and it still won't trip the excess flow valve. So those are some things to consider. So in this particular case, we could have used a Series 775 half CTS, but it would protect only 45 foot of line and only 39 foot of line if you wanted to keep 6 psi at the regulator. So I'm not saying this is the only solution. This is just based upon that example that we gave with the chart. It may be that a particular company would be fine with a shorter service line protection because all their services are 25 feet long or something like that in a particular area. So they might have different considerations. But whatever it is, you just have to make sure that you have selected that series and the valve and the pipe size so that you do cover the entire length and keep the parameters that we talked about earlier with the pressure at the regulator and the trip point above the anticipated load. Okay, so quickly let's go into a couple other features on the calculator. The calculator will also let you calculate or estimate the time it's going to take to reset. As we just talked about, if you have a procedure where you open your line up after installation, purge it, and you do trip your excess flow valve because you want to verify that it's working correctly and it's there, you then have to allow a particular time for it to reset. And we found that this also has been an area early on as excess flow valves became more and more prevalent after they were required, where there were some issues that appeared in the field thinking that a valve was not operating properly, and upon investigation determined that the valve was just not being allowed to reset. In other words, not enough time was being given for a valve to reset. Remember, we said there's a bypass on these valves that's basically a fixed restrictive flow rate, and that's fixed at the factory. And with variation in manufacturing processes, it can vary a little bit on what that orifice size is to allow that bypass. So the calculator will help you set up tables much like you did for sizing for expected reset times so that you can give those to your crews if you so desire and determine what might be appropriate time to wait for a particular installation characterization or configuration. So we'll look at this section right now. It has a place to put in your system pressure. So when you're looking at reset times, you want to look at the system pressure that is, I would say, normal or nominal, or what is expected to be in play as the valve is being installed. Not necessarily the system's minimum expected on an annual basis, but what is it that you expect to be present when it's being installed, because that has an effect on that reset time. And then the service line length in feet. And here you notice we didn't use equivalent feet, we used feet, because really what we're looking at is a volume and pack of a line. So we're looking at the actual length of that service line size. This particular portion of the calculator is still using the service line size that was selected at the pull down here at the top of the calculator. So all the numbers you're putting in here are going to be calculated upon that service line size that was selected above. So don't forget about that. If you're going into the calculator and just utilizing this section, make sure you set the service line pipe size to the one that you're wanting to calculate on. And then you can see there's two result boxes here. One's preset to 45% maximum allowed bypass. What that means is the bypass flow rate, as we said earlier, is 20 standard cubic feet per hour at 10 psi maximum flow rate. So this is looking at a 45% of that as a level of bypass. But it allows you to look at even less or more conservative numbers as you're building your tables, and to see the effect of those changes. Now in this example here, I put in 30% of the maximum allowed bypass. This would be a more conservative number, meaning you don't know on a particular valve, even though most of our valves are designed to have a bypass flow rate in that 50% area, between that 45, 50, 55%. Because of the manufacturing variations, it can vary. And so you can have a valve that might be a little bit lower than that on one valve to another. So here if we put in 30, and you can see that on this curve represents the time for reset. And you can see at 30%, that's you're coming off this flat portion of the curve and starting in the exponential portion of the curve as far as the effect on time. So at a 30% level, it's going to be a longer time. If you calculate it out, it would be 20, in this particular case, at 40 psi and 240 foot of line, it would be 15 minutes and 26 seconds estimated to reset that valve once the breach or whatever opened to atmosphere was fixed or closed off, or the valve was closed if it was a case of just purging out your service line. Where if you're calculating on 30% bypass flow for that particular valve, it's going to be 23 minutes. So again, you can decide on how conservative you want to be as you're building these timetables, so that you can give guidance to your crews on just how much time that they should wait before trying to open the valve again partially to make sure there's flow in the service after tripping the excess flow valve or after purging the line. What can happen is if you don't leave enough time, if you're not conservative enough, and your crews don't wait long enough or within the time that they've been given, and the valve has not reset, what happens is you get into a bit of a loop, because then it's noted as the valve is opened by the crew that gas is not flowing. So, gee, there's a problem. They close the valve, and again, they begin to wait. But as we all know, the second time you wait for something, you're not near as patient as the first time. And so the next time they go to check the valve, they open it again, they find it's still not flowing. And that's because once you open the valve, you're kind of resetting the time. You have to really wait the full amount of time again for the valve to reset. And oftentimes what we've found is you get into a little bit of a loop, and the determination is made that the valve is not functioning properly, when in fact it does, and it is, and it will reset, but not enough time was given. So this can be a very helpful tool in setting those expectations for your crews if you want to build that table. So let's look at a table, what a table might look like for that. Here we have a table for reset times specifically, and this is at 40 psi pressure, much like what we were just looking at. And if we looked at that 240 feet of the one CTS service, or you can see on the table you got half CTS service, one CTS service, inch and a quarter. The table also has 2 IPS. But in that range of the 240 foot service line length, 23 minutes and 4 seconds. That looks familiar because that's what was on the calculator. But that would say if your crews are using an excess flow valve on a 1 CTS service, and your pressure is 40 psig is what your expected service pressure is, up to 240 feet, you should wait 23 minutes and 4 seconds for the valve to reset before checking to see that it actually did reset and is functioning properly, so that you don't get into this oscillation in the mode where you keep checking and the valve never has a chance to reset. So these tables can be very, very useful, and you can use, again, this is just one example, whatever your conditions are, you can build these tables for your conditions and then give that guidance to your crews. if I can pop back into the calculator real quick, that's this section down here on the calculator. Again, we'll look at that, I guess we were looking at 1 CTS line here, 40 PSI, I think we were looking at 240 feet or something like that. And it's that 30%, which that table was built on that 30% conservative number of the bypass flow. It's 23 minutes and 4 seconds. So you could use whatever number you wanted here. If you wanted to use something other than 65%, and you wanted to use 45%, you could use that as well. So you can do whatever you need to do. If your system pressure is 25, certainly you can change that to 25. And maybe you're only looking at 150 feet. And maybe you're looking at, oh, I don't know, look at 1 IPS line or something. And then it'll give you the time for those conditions on that service size. Now, as you can imagine, as you get into larger service line sizes, let's look at a 2 IPS. Again, as we're looking at these larger flow applications and larger excess flow valves, you can get into some pretty hefty times, especially if you're looking at some fairly long services. 1,000-foot service on a 2 IPS pipe with an inlet pressure at 25. Let's go 45. You're looking at almost 5 hours at a 45% flow rate. If we went conservative to 30, 7 hours to reset that line. So again, as you're getting in, if you're getting into large services, large sizes, long lengths, you're probably going to be looking at different procedures for resetting or for activating these valves to wait for a reset, or possibly back pressuring them to reset them rather than waiting for the automatic reset. Just to give you an extreme, if we did something real extreme like 4,000 feet or something crazy like that, now you notice it's 5 hours, 31 minutes and 30 seconds, but no, it's 1 day, 5 hours, 31 minutes and 30 seconds to reset that line through the automatic reset. Because again, this is a fixed orifice, it's very, very small, and you're trying to pack out a 2 IPS line that's 4,000, 3/4 of a mile long with that small flow rate, and it takes a long time to get it back to equalization. So as we look at the larger flow rates, larger pipe sizes, this is something that obviously has to be considered and looked at as far as your operation procedures for resetting and possibly even for forcing a reset at the time of installation. Okay. So let's pop on back here. Well, actually, I've come kind of the end of my plan presentation, and we've got, I guess we're about 1 hour and 7 minutes. We have a little bit of time before we used up all the time that we allotted. If there's any questions that people have been storing up and wanted to ask, we can certainly take a look at those at this time.
Hi, we have Russ who has a question. Go ahead, Russ. I am going to unmute you.
Hey, can you hear me?
Yes.
Yes.
Okay. I was just noticed there that on your presentation you have version 7 of the Lyall calculator.
Yes.
And I was looking online, I could only find version 6. I was wondering if that's available, the one that you kind of just taught us on here, or if that's anything that's somewhere else besides the website that I wasn't able to find.
Yeah, 7A is brand new, and I am releasing it with this webinar, so you'll find it on the web page after this webinar. It will be available.
Okay. That's all I had.
Thank you. Any other questions out there? Okay. Maza, you're online. Go ahead. Maza.
Hello, did you have a question? Maybe we unmuted the wrong line.
No. Mazania.
Was it a text question?
No, he just raised his hand.
Okay. Anyone else?
Hold on one second. Okay, Maza's question is, what is the design life of a Lyall EFV?
What is the design life? Well, the EFV is designed to last as long as the service. So the valves are tested for thousands plus cycles. Obviously, an EFV is not going to see that. And as far as the service life of the components, it will last. It's designed to last as long as the service pipe that it's inserted into.
Okay. There's another text question from Maggie, and her question is, series installation of EFVs okay?
Yeah, I think that question goes to handling of services that may be where you're. I'm trying to think of the word now. I'm not coming up with it. Where you're going to two different structures off of one service line coming off the main, and that's certainly possible. There's nothing that restricts that being done in the design of the access flow valve. Of course, it does put some complication into the sizing considerations as you look at that. You would, if you're looking at branch services where you have two structures that have particular loads, each of them have their own expected loads, you obviously have to design the trunk portion of that service, or what would be the main or pre-branch portion of that service, to be able to handle the length with the pressure drop. That it can be severed anywhere along that length of service, and the excess flow valve would then have to be able to handle both of the loads for those two structures as far as sizing for the trip point. So you want the trip point above the aggregate loads for both structures for the EFV that's back, protecting that trunk portion of the service. And then, of course, you could put another excess flow valve on each branch, meaning the excess flow valves would be in series to protect that particular structure, or the service up to that particular structure. There's nothing that would prevent you from doing that, but you would obviously have to just take care in the sizing of each section of that service to make sure that all the same considerations that we talked about here today are being met. I don't know if hopefully that answers the question.
Are there any further questions? Okay, it doesn't look like there's any other questions coming up right now. Hold on one second. If you do have questions, you can use the little hand icon on the right side of the screen. It's a little blue circle, and then Greg can answer your questions.
Well, if there are no other questions, that's fine. You can always reach me here at RW Lyall. shoot me an email or give me a call if you have any questions. You can also contact a Lyall representative for your company, and they'd be happy to direct any of your questions back to us that we can answer. I want to thank you all for joining us today, and hopefully this was helpful, and it's something that we would like to continue to do in the future. So thanks again for joining us and for being a part of this webinar. And if you have any questions that come up afterward, again, just go ahead and drop me a line. Notes will be available on this webinar, note pages of the presentation, probably within the week. And again, as I said earlier, this particular version of the calculator will be available online after the webinar. It will be posted to the website. All right, have a great afternoon. Thank you, everybody.